Hello class, welcome to this lesson on the second lesson of the unit. We're going to be talking about exponential models today. So we're going to talk about how to write exponential models in different ways to solve a variety of problems. So how can we develop exponential models to represent and interpret these situations? So we're going to be talking about compound interest as well as continuously compound interest in the natural base e as well as other things. So recall that an exponential function is of the form y equals a times b to the x, where b can range in, where b and a you can generally be most numbers, except for 0, and in the case of b can't really be 1 for it to be called an exponential function. However, there are a couple cases for b that we want to consider. If b is greater than 0, then this should actually be greater than 1, not 0. So if b is greater than 1, the exponential function actually represents growth. So if b were like 1.5 or 2, then that exponential function will represent a increasing trend or a growth. If b is between 0 and 1, such as a fraction like 1/3, 1/2, 1/4, etc., the exponential function actually introduces a decreasing trend, which represents decay. So in applications of exponential growth or decay, when we're actually using this, we want a model to be able to express, the growth or decay in that situation. And so what we do is we take the y equals a times b to the x, and generally x is considered time, so we replace x with t for time. We want to see the trend over time. And in order to express growth or decay, we replace b with this expression, the 1 plus or minus r. Now the t represents time, as I mentioned earlier, a represents the initial amount, r represents the growth or decay rate. So how fast is it growing or how fast is it decaying? And usually it's given as a decimal because the rate is given as a percent, so like 5% increase. The plus sign indicates that we're using an exponential growth model, and a minus sign indicates that we're using a decay model. So let's look at an example. Let's say you have a 50% increase in your salary every year, which is pretty high, if your starting salary was $30,000. So year one, your salary was $30,000, and they're going to increase it by 50% every single year. What would be the exponential model for this scenario? Well, remember, we're going to be using the a times b to the t instead of b to the x. Then we'll go ahead and replace the b with the 1 plus r. Now we're using plus because we're talking about growth, right? We have an increase in our salary. And r is 50%, which if you convert that to a decimal is 0.5, which is why we got 0.5 in our model. So we got 1 plus r to the t power. Now this can be expressed as y equals 30,000 times 1.50 to the t power. So that is our exponential model for this scenario. Now in this case we said r is the growth rate plus 0.5. We use t instead of x for time, and 30,000 is the initial salary. So what will be our salary after 5 years? Well, then all we got to do is plug in 5 into the model for time. In that case, we have $227,812.50. That is some raise after 5 years. Don't we all wish that to happen? So now what we're going to do is we're going to actually take this model of the salary and the 50% increase, and we're going to show how it changes over time. So initially at x equals 0, or I guess we should say time instead of x, but you get the idea. If time is 0, then we're going to get $30,000, for that year. Then we get a raise after 1 year, and so we get a 50% raise. So a 50% increase will lead us to have a salary of $45,000. How do you find that? Well, you just do 30,000 times 0.50, and that's going to give you $15,000, and then you can add that to the 30 to give you 45,000. So basically, you're taking half of the salary and then adding it to the original salary. That's a 50% increase. Then after the first year, or after 1 year, so now 2 years, you're going to have another 50% increase. So meaning you take half of 45,000, you add it to the original, you're going to $67,500. Then after 3, 4, 5 years, you can see the final answer that we have, $227,000. Now, if this trend increases, then this is going to be exponentially increasing, right? So this is why we call it an exponential function. In this case, we're multiplying by 1.5 every single time to get to the next number. All right, so now let's look at the opposite scenario. Instead of looking at it as an increase, let's look at it as a decrease. So there's a 20% decrease in the elephant population worldwide each year. So let's say 20%, we're just coming up with that number, due to the increase in deforestation, hunting for elephant tusks for ivory, etc. There are a variety of reasons why we're losing the elephant population. And one of it is we're expanding into territory, and therefore we need to deforest areas, and therefore it's messing with the the ecology, the environment of the elephants, etc. If the elephant population was about 400,000 in the beginning of 2010, how many elephants will be present in the beginning of 2021? So notice that's a difference of 11 years, right? So after 11 years, what would the population become if it follows this exponential model? So we're going to need to come up with the model first, right? So the model for the elephant population can be given by 400,000 times 1 minus r. We're using minus because we're doing a population decrease, and this is our 20% decrease in the elephant population. So that becomes 1 minus 0.20, which is 0.80, okay, which is our model. So once we come up with that model, we want to plug in 11 for the time, because the difference between 2021 and 2010 is 11 years. And therefore we get 34,359.7 elephants, but it doesn't really make sense to have a decimal for creatures that we're talking about. So we're going to round it to about 34,360 elephants, which is pretty small. And therefore you can kind of see why if this trend were to continue, then we're going to see extinction of a species, right? And therefore we want to be able to preserve those animals. All right, so in 2015, the population of a small town was 8,000 people. The population is increasing at a rate of 2.5% per year. Rewrite an exponential growth function to find the monthly growth rate. So we know that the initial population is 8,000. We know that the rate of 2.5% can be converted to a decimal, 0.025, and that will become our r in our formula. So we plug that in. So 1 plus r, we're dealing with a plus because we're talking about a population increase, okay? So therefore we have our exponential model. So now, since this is per year, right? This percent is 2.5% per year. What we want to do is, we know that there are 12 months in a year, right? So 1 year can be written as 1 over 1, and then if we convert that in terms of 12, right, that would be 12 over 12. So there's 12 months out of 12 months. That's 1 whole year, right, if you did it for 12 months. Okay, so what we're going to do is break up the 1 in front of this t here. There's an invisible 1 there, right? We're going to convert that to a 12 over 12. So we put that there. All right, and that's because we want to break it down monthly, right? So 12 months out of 12 months, that's 1 year. And then what we're going to do is we're going to now split the 12 on the bottom, and basically bring it to the 1.025. Now that 12 on the bottom has an invisible 1 on top, so I write it as 1 over 12 power. And then we still got the 12t, left over. All right, so now we know that we can calculate what 1.025 to the 12 power is. That's this inside here. We can calculate that. That's just the same thing as the 12th root of 1.025. You can do this on the calculator, and you're going to get this number, 1.00206. So if we take that number and plug it back in there, then we get our new exponential model, which is based off of monthly growth, okay? All right, so now we converted something that was annual to something that is monthly, all right, 12 times a year. So now what we're going to do is we're going to take the new number that we got, the 1.0026, and we're going to subtract it from 1 to get the amount of growth that was happening. In this case, the amount of growth is 0.00206, which is converting to a percent. You got to move the decimal place twice to the right. You're going to get 0.206% per month. All right, so notice that to find that monthly rate, we didn't just take the yearly rate and divide it by 12. So you may be asking yourself, if we're trying to find the monthly rate, can't we just take the year rate, 2.5%, and divide it by 12 and to get our answer? Well, the answer would be no, because that would actually be an incorrect measure, because remember, we didn't get 0.2083, we actually got a different number. So the pattern seems to be able to raise the inside, the 1 plus 0.025, to the 1 over 12th power, and then subtract from 1. So the pattern seems to be you include your growth rate, you add it to 1, right? But just like in the formula, and then you raise it to the 1 over 12 if you're talking about monthly, and then subtract it by 1. And then you get 0.206%. Now notice how these numbers are different, right? So you can't just divide by 12 and get the correct percentage. Although they're pretty close, it's still technically not correct. So the difference is not that much, but it is still incorrect to divide. So now to find the rate every 4 months, you simply raise to the 4/12's power. Since we're talking about the rate every 4 months and not every month, if it was every month, that would be 1 month divided by 12 months in a year. This time you're talking about 4 months, so it's 4 months divided by 12 months in a year. So 4 over 12, or 1/3 power. You can reduce that to 1/3. So we take our 1 plus 0.025, we raise it to the 1/3 this time. We subtract 1, and then we get this decimal. Move the decimal place to the right twice, and you're going to get 0.83% for 4 months. All right, pause the video, see if you can try the following problems. All right, so the population in a small town is increasing annually by 1.8%. The initial population was 2,000 people. What is the exponential model for the town population? All right, so we know that the R is 1.8%, which is 0.018. You got to move the decimal place to the left twice to get that decimal. And then we're going to plug that into R in the formula, and we're talking about an increase. So we're going to be using a plus sign right there. Then we add those two together and we get 1.018, and that's our exponential model. Next up, we're talking about the population after 15 years. So now we know we could take our model and plug in 15 in for time. And then we do that in the calculator, we get a decimal, but that decimal doesn't make sense if we're talking about real life people. And so we're going to round it to about 2,614 people, which is still not very much after 15 years, but keep in mind that the increase is only 1.8%. So that's a very small growth rate, which explains why there are still not that many people after 15 years, if this model continued. All right, so now part C, what is the quarterly rate of the population increase? So if we want to find the quarterly rate, that's every 4 years, right? That's every fourth time per year, so 4 times per year. So the quarterly rate is 1/4 of a year. So convert 1 year to 4 over 4, 4 times in a year. All right, so if we're doing it 4 times in a year, this also means if you're talking about 4 times a year, that's really every 3 months. So you could also have used 3 out of 12, which is still going to be 1/4, right? 3 out of 12 months is still going to be 1/4. So you could also use that. So then what we do is we convert the 1 year, the 1 over 1, into 4 over 4, which is right here, 4 over 4. And then we move the bottom 4 to the 1.018. But then there's still that invisible 1 on top. So basically the 4 over 4 becomes, we can move that over, but if we move it over, it becomes 1 over 4, and then times the 4 from there. So this is the 4 from here, This is the 4 when we move that bottom one over to the, other side. And so that's how we get the 1 over 4 right here. And then we do that on the calculator. We get 1.0045 to the 4t. Then we calculate that, so the quarterly rate. So we take this number, we subtract 1 from it, and we get the rest of it. This should actually be, let's round this. This is 0.0045, which is rounded. The more accurate, or the more precise measure is 1.00447. I rounded it to 45, but let's be more accurate with it. We get 447. Okay, so we move the decimal place to the right. I'm sorry. If we move the decimal place to the right here, then we get 0.447% per year. Per 3 months. I apologize. Per 3 months, which means per quarter. All right, so when you borrow money from, so we're going to talk about compound interest. So when you borrow money from a bank, a lender, like a credit union, a financial institution, you need to pay the money back plus interest. Generally, this is the case for most times you borrow a loan. Now, there are some cases where you can borrow money without an interest rate, without paying back interest, but that's very rare, and it's usually for a small length of time. Most of the time, you have to pay the money back plus interest. So the amount of interest paid back actually depends on the interest rate. We also call this the growth rate in mathematics terms, right? The original amount of money borrowed is the principal. So that's how much money you borrowed in the beginning. Now, because interest is added every so often, this amount gets added to the principal. So your new principal is now bigger than it was before. Now, because the principal is bigger, now you get charged more money the next time more interest is added because the principal is larger. Therefore, the interest next time will be larger, and this will increase in a cycle, right? So the principal gets larger, and therefore the interest gets larger, and then next time interest is applied, the principal got larger, and so the interest is now larger. So this just compounds, right? It just gets bigger and bigger and bigger. So we call this growth of interest over time compound interest. So let's talk about an example. So let's say you borrow or you pay $2,000 in a credit card. Well, when you're paying on a credit card, you're really borrowing money from a financial institution. So you're really borrowing $2,000 from the bank. And let's say you wanted to do that to pay for car repairs. Suppose a bank charges an annual interest rate of 22%, which is pretty high, although it is common if you have an experience of low credit score, or for some banks, they tend to charge high interest rates. So let's say that your interest rate is 22%. Well, then let's say interest is compounded every year. So let's say interest is being charged every year. After 1 year, you're going to owe 2,000 times 1 plus 0.22. This is because 22% gets converted to a decimal. And then, using that formula, right, after 1 year, then you're going to owe $2,440. Notice that this is more than you borrowed a year ago, right? How much more? Well, $440 more, right? So that amount that was added to your initial principal of $2,000 is the interest, $440. So now your principal is larger, $2,440. So now you owe that much at the end of the year. All right, so after another year, now you'll owe $2,440. You take that interest that got larger, and now you're going to apply that to the formula again. So now you owe $2,976.80. Even more. So that's after 2 years. So after the second year, that's how much you owe. Now, how much more is that from the first year? Well, this actually represents an increase in interest. The interest went from $440 to $536.80. It didn't just add another $440 to it. It actually added $536.80 to it instead of $440. And this is because 2,976 minus 2,440 gives us 536 from the previous year. Now the interest grew from 440 to 536. Why did it grow? Well, it grew because the principal got larger, right? And this is going to keep happening if you're not making payments to that, right? To that credit card. Let's say you're not making payments on that credit card for that entire year. then you're going to owe 2,000 plus 440. And then if you're not making that payment after the first year, then you're going to owe $536 more, so 2,976, and so on. And this is going to compound and compound and compound. And this is an example of compound interest. So how do we calculate it? Well, the compound interest formula is an exponential model to calculate the value of an investment when interest is compounded. So the formula is given over here. So this is A equals P times 1 plus R over N raised to the N times T. So the P is the principal that was invested, the amount of money that you borrowed, or let's say the amount of money that you invested in a savings account or something like that, in a stock. Now R is equal to the interest rate written as a decimal. Usually they give you that to you as a percent, but you got to convert it to a decimal. N is the number of times that you're compounding. So if you're talking about annually compounding, that would be 1 time per year. If you're talking about quarterly compounding, that's 4 times per year, etc., etc. Now A is the value of the account after T years. So A is either the value that the amount that you owe after X amount of time, or the amount of money that you get back after X amount of time, if you're talking about like a savings account or something like that. Now notice that instead of using y here, we used a, right? Notice that the formula was y equals a times 1 plus r to the t. So we use big A for y, and we use big P for little a. And then of course we have the number of times that we compound, which is given by n. So the formulas are pretty similar. So let's look at an example. Terry invests $5,000 in an account that pays 4% annual interest. How much will there be in the account after 3 years if the interest is compounded annually, semi-annually, quarterly, or monthly? So we have different compounding periods. So use the compound interest formula to find the amount in Terry's account after 3 years. So what we're going to do is we're going to come up with a chart for the annual, semi-annual, quarterly, and monthly. So let's do the annual. So annual means that you're doing it 1 time per year. So the number of compounding periods is 1. So notice that the N is 1. And the T is the time after 3 years. So we plug that in for the time after 3 years right there for 3. Okay. The principal is $5,000, right? Given right here. This is how much he invested. The interest rate is 4%, which is 0.04, which we plug in there. Okay, so this is how we get the numbers. Remember, so I'll write out the formula, 1 plus r over n to the nt, and then we plug those numbers in. All right, so now we're going to do it semi-annually. So semi-annually means n equals 2. You're doing it 2 times per year, and therefore this is going to be 2. We do that, we get $5,630.81. Quarterly represents n equals 4. You're doing it 4 times per year. Monthly is going to be 12 times per year. So we use that formula for 12, and we get, so these are the values that we get for annual, semi-annual, quarterly, and monthly. So notice that as the number of compounding periods increases, the value increases, the value gets bigger. And that's the pattern that I want you to see there. However, it grows really fast in the beginning. In the beginning it goes really fast, and then it doesn't grow as fast. That's going to be a pattern that we're going to see in the next lesson, in the next slide actually. So now consider an investment of $1 in an account that pays 100% annual interest for 1 year. Find the value of the account for the number of compounding periods given. All right, so this is the formula for the compound interest. Now we know that T is going to be 1, right? Because we're talking about 1 year. So that's T equals 1. We're also talking about the principal being 1. So that's big P, right? So that's going to be right here, big P. We know that the interest rate is 100%. So 100% means R is equal to 1. All right, so 100% is 1. So that's why we plug in 1 for R right there. So then we get this formula right here, 1 plus 1 over n to the n power. So that's our formula. Now what we're going to do is we're going to use this table and do it for 1 compounding period. That means annually. 10 compounding periods. That means 10 times per year. 100 times per year, 1,000 times per year, 10,000, 100,000 times per year. How much does the value increase if you're applying interest this often? All right, so let's look at the first one. So if you plug in 1 into the formula for n, you're going to get 2. So that means after you invest $1 into that account, you're going to get back the value of that account will now double, and it'll become $2. Okay, so it'll become $2 after if you're compounding interest once. Okay, once per year. So at the end of that year, it's going to be $2. Now, what if you're compounding the interest 10 times per year? What will the value be after 1 year? Well, then you're going to plug in 10 into the formula for n, and you're going to get, so at the end of that year, so after 1 year, you're going to get $2.59. That's how much the account is going to be at the end of that 1 year. Now, if you invested $1 and you compound the interest 100 times, how much money is there going to be in the account after 1 year? After 100 times of compounding interest, the value is going to be $2.70. You can see that's not that much, that's not that big of a deal, right? You know, from one time it's $2. 10 times, okay, that's pretty significant, you know, somewhat, you know, it's more than half a dollar. And then after 100 times, which is 10 times more, you only get, you know, like 11 cents more or less, right? So now what happens if you do 1,000, 10,000, 100,000? Well, if we do that, the difference that we get is marginal. It's very, very small difference in how much money we get when we do it that many times. So you can see that there is a diminishing return here, right? There's less that we get after we, you know, increase the number of periods. Yes, technically it's more, but it's more in the thousands, 10,000s, 10 millionth place, which doesn't really do anything to the account because this is still going to be worth $2.72 when you round it on the bank, right? It's still going to be worth the same amount. So this number right here that you see, the 2.718 number, is a very special number indeed. If you increase the amount of compounding periods, the value of the account increases technically, but it still remains very close to 2.718. And that number is a special number. This special number is called the natural base. So the natural base e is defined as the value that the expression 1 plus 1 over x to the x approaches when x approaches infinity. So in this case, it's 1 plus 1 over n to the n. That was the formula that we had in our example. But as the number of compounding periods increases, this formula approaches 2.718 dot dot dot. So, you know, 1,000, 1,000,000, 1,000,000,000 times, it'll still approach 2.718. And this number is called e, and e is kind of like pi. It's an irrational number. So there is no pattern to the numbers in e, just like there's no pattern to the numbers in pi, and they go on forever. So therefore, it is called an irrational number, and this is my e, 2.718281828 dot dot dot. There's no pattern to it if you continue the digits forever. So now you know a new number, e, kind of like pi. And e is a number for growth. So now remember, what we did in the previous example is we kept compounding for more and more periods. 1, 10, 100, 1,000, 10,000, 100,000. So as we continue the amount of compounding periods to infinity, we call this continuously compounding, which means you're continuously doing it. So it's infinity. Okay, so how do we calculate that if we're doing it to infinity, the amount of interest? Well, we call this continuously compounding, and we use the number e for that. So we use the continuously compounded interest formula to calculate this. So notice that instead of having the p1 plus r over n to the nt, now this now becomes e, right? So now we have e there, and then the r goes to the exponent. Okay, so now the formula for continuously compounded interest is a equals PERT. I like to think of it as PERT. It helps you remember it. So a equals pe to the rt. P is the principal, e is the natural base, the 2.71828 dot 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 number, and R is the rate, A is the value after 10 t years. All right, so let's look at an example. So Regina invests $12,600 in an account that earns 3.2% annual interest, compounded continuously. So it's doing it, multiple times, infinity, 100,000, a million times, etc. What is the value of the account after 12 years? Round to the nearest dollar. So we know that this has to be our principal, right? How much we invested in an account. This is the amount of interest we get back. So 0.032, we got to convert that to a decimal, move that decimal place twice to the left. And then this is clearly going to be our time. So we can plug those into the continuously compounded formula, the A equals PERT. So that's our principal, R is our interest rate, and T is our time, which is 12 years. And this is how much we're going to get back. So the value of the account to the nearest dollar is $18,499. So pretty significant, but keep in mind that the 3.2% annual interest is still kind of low. I mean, it's a good interest rate nowadays, but it's still kind of low because you're gonna get $6,000, less than $6,000 in 12 years. 12 years is a pretty long time. All right, guys. So that is it for the video. I hope you learned something new or a couple things, and I will see you in the next one.